Hello everybody and welcome to my talk on deep declarative networks with application to optimal transport. My name is Stephen Gould and I'm a Professor of Computer Science at the Australian National University. Let's start by going back about 200 years. On the 1st of January 1801, Italian astronomer Giuseppe Piazzi discovered Ceres, a new planetoid or dwarf planet orbiting our solar system. Now, Ceres was too small to see by the naked eye, but Piazzi managed to track the planetoid, making 24 observations over 40 days using a telescope. He continued to make observations until Ceres became occluded by the Sun. So a number of astronomers were really interested in rediscovering Ceres as it came out from behind the Sun, but they lacked the mathematical tools to be able to predict its orbit. Now, this piqued the interest of another mathematician, Carl Friedrich Gauss, who developed models of planetary motion and used the least squares method that he'd developed a few years earlier to fit Piazzi's observations to his models and therefore allow astronomers to be able to retrack Ceres as it came out from behind the Sun. And lo and behold, on the 31st of December 1801, another astronomer by the name of Franz Xaver von Zach was able to locate Ceres exactly where Gauss had predicted it to be. So that was perhaps the first instance of optimization in science and engineering. And today optimization is everywhere. In financial mathematics, we look to maximize profits or minimize costs, subject to constraints on resources or budgets. In mechanical engineering, we do things like maximize the span of a bridge, subject to load constraints. In electrical engineering, we want to minimize the size of a transistor in a circuit, subject to power and timing constraints. In logistics and planning, we want to do things like find the cheapest way to distribute goods from suppliers to consumers across a network. In statistics and data science, we use optimization for curve fitting and data visualization. And of course, in machine learning and deep learning, what we want to do is minimize loss functions with respect to the parameters of our models. So I'm now going to talk about differentiable optimization, and to do that I'm going to introduce this idea of bi-level optimization or Stackelberg games. So we consider two players, a leader and a follower, and they're producing goods in a market, and the market dictates that the price it's willing to pay for the goods based on the supply, that is the amount of goods produced by the players, and that is some function P of Q1 plus Q2, which is the quantity of goods produced by the leader and the follower. Each player in the market has a cost structure associated with producing goods, that's Ci of Qi, and wants to maximize its own profits. So that's the number of goods it produces, Qi, times the price that the market's willing to pay, minus the cost of producing those goods. Now, the leader is going to go first, knowing that the follower will respond optimally. So the leader wants to produce a quantity of goods that maximizes their profit, subject to the follower then producing an amount of goods maximizing their profit. And this leads to what's called a bi-level optimization problem, where at the upper level, the leader is maximizing their profits subject to the follower producing a quantity of goods to maximize their profit, knowing the quantity of goods that the leader chooses. In machine learning, we also have these bi-level optimization problems, and here the quantities that we are reasoning over are the input x, the output of the model y, and the parameters of our model theta. And what we want to do is we want to minimize the loss over the parameters of the model, subject to y, the output, being the solution to a parametrized optimization problem, where the lower level problem is parametrized by the input and the model parameters. And the way we solve this bi-level optimization problem is through gradient descent, where we need to compute the gradient of the lower level solution y with respect to the parameters theta, using the chain rule to get the total derivative. And we can do this by backpropagating through the optimization problem. So let's go back to our least squares problem. Formally, the least squares problem is to minimize the objective of the norm squared of ax minus b. This has a unique solution if A transpose A is invertible, namely the solution x star equals A transpose A inverse times A transpose B. And that's usually solved using QR factorization instead of forming A transpose A inverse explicitly. If A transpose A is not invertible, then we can still get a solution using the SVD decomposition of A. And in fact, there are multiple solutions in this case. So we can get one solution, x star, and then we can add to that any vector from the null space of A, and that also gives us a solution. And normally this is solved using an iterative solver. So now the question arises, well, what happens if we want to differentiate a least squares problem with respect to the parameters A and B of the problem? So we know that the least squares problem has a closed form solution, which is x star equals A transpose A inverse A transpose B. And so now what we can do is we can differentiate this solution with respect to any of the parameters. For example, with respect to the element, the ijth element of the matrix A. And after a little bit of algebraic manipulation, as well as combining with the incoming gradient of the derivative of the loss with respect to the solution x star, we get these expressions here for the gradient of the loss with respect to the parameter matrix A, or the gradient of the loss with respect to the parameter vector B. The quantity A transpose A inverse is used in both the forward and the backward pass. So it's used in both solving the problem to compute x star, and it's also used in computing the gradient. This means that we can factor A once into its QR decomposition. We can cache the value of R, and we can reuse that when we're computing gradients in the backward pass. So I'll give an example of code for doing this, but just before we do so, a quick aside to talk about how PyTorch and other deep learning frameworks operate on batch data. So usually instead of processing one example at a time, these deep learning frameworks will process data in batches, and they are passed as tensors into the functions that do the processing. So for example, if we were to compute the quantity y equals ax plus b, we might have k different values for x, so x1 up to xk, and then the output would be a tensor which has the quantities ax1 plus b, ax2 plus b, all the way up to axk plus b. Okay, and a lot of the PyTorch functions are batch aware, and for many operations we can use the iXsum function as well as, the INSUM function as well as broadcasting. So here's an implementation of the forward pass for computing least squares. So the first thing we do is just a little bit of housekeeping. Then on line 9 we tell PyTorch that it doesn't need to do automatic differentiation. We're going to provide our own code for the backward pass. Then on line 10, we perform the QR decomposition of A. We then use a backsolve to solve for X, which is effectively computing R inverse Q transpose B. Okay. Then on line 15, we just save some information for the backward pass, and we return our solution X. In the backward pass, we now need to compute the gradient of the loss with respect to the parameters of the problem, which are both A and B. We do this using the expressions that we derived earlier. And note that this is a very, very short amount of code that allows us to compute both the solution in the forward pass and then the gradients in the backward pass. And the other thing to note is that we're reusing computation from the forward pass. So in particular, we reuse the solution that we found, X, as well as the decomposition of A into Q and R. We don't need Q in this case, we just need R. All right, so let's switch gears a little bit and talk about deep learning. And the way I like to think about deep learning is as defining a function or a model in terms of a set of smaller, simpler parametrized functions. So our model is composed of these very, very simple parametrized functions. And you can think of the model as being defined by a computation graph, and these simple parametrized functions within the model as being nodes within the graph. So here I've shown an example graph. It has two paths, a top path and a bottom path, and it takes x through this series of functions to get to the output y. And we can write this mathematically as y equals this composition of functions of f8 being composed with f4 and f3 and f2 and f1 and so on, and another argument f7 composed with f6, f5 and f1. And here I've omitted the parameters theta I just for brevity. So in the backward pass, what we need to do is we need to compute the gradient of the loss function with respect to any of these parameters. And we do that using the chain rule of differentiation. So here I've just shown an example of computing the derivative of the loss with respect to parameter theta 7. And that's going to be the derivative of the loss with respect to the output y times the derivative of y with respect to z7, which is the output of function f7, and then times the derivative of z7 with respect to theta 7. Okay, and we just multiply those together using the chain rule of differentiation. A slightly more involved example is if we wanted to compute the derivative of the loss with respect to theta 1. And now we have to consider two different paths and sum up the gradients over those two paths, as I've shown here. Okay, but again, this is just high school calculus using the chain rule of differentiation. So in short, a deep learning node within this computation graph has two operations. In the forward pass, it computes the output y as a function of the input x, as well as model parameters theta. And in the backward pass, it computes the derivative of the loss with respect to the input x and model parameters theta, given the derivative of the loss with respect to the output y. Now, automatic differentiation, of which backpropagation is one example, is an algorithmic procedure that produces code for computing exact derivatives. It assumes that all of our numeric computations are composed of a small set of elementary operations that we know how to differentiate. So for example, arithmetic operations, exponentiation, taking logarithms, trigonometric functions, and so on. And it's the workhorse of modern machine learning. It greatly reduces the development effort in building new models, in particular layers within a deep learning model or nodes in a computation graph. There are two flavors of automatic differentiation. There's forward mode automatic differentiation, which propagates results on a first order approximation to the data, so x plus a delta x. And then there's reverse mode, which is perhaps more popular, and that builds a program to compute the derivative based on the chain rule of differentiation and reusing computations where applicable. For example, in our code for differentiating the least squares problem, we reused calculations from the forward pass. And different deep learning frameworks use slightly different approaches, but they all build on one of these two different flavors. So here's a toy example of what we might expect from automatic differentiation. And this is an algorithm known as the Babylonian algorithm. And here I'm showing the forward pass for that algorithm. So we start by taking the input x, and we assign y0 to be half of x. And then for iterations t from 1 up to capital T, we assign yt to be half of the previous yt minus 1, plus half of x divided by yt minus 1. And we keep going for t iterations, and then we return y capital T. Now, each of these steps is a differentiable step. And so we can, automatic differentiation can automatically generate code for the backward pass, which given the derivative of the loss with respect to the output yt, it will go and produce the derivative of the loss with respect to the input x. And it does this essentially by unrolling the forward pass operations and then computing the gradient using the chain rule going backwards through those operations. Now, some of you may recognize this algorithm as being the Babylonian algorithm, and it computes the square root of a number x. And so knowing that, we can actually shortcut the backward pass function and recognize that the derivative of the output y with respect to x is 1 over 2 times the square root of x, which equals 1 over 2y, and we could code that up explicitly. The point here is not about the efficiency of the implementation, but the fact that automatic differentiation can go through and automatically generate this backward code for us. But there are some instances where automatic differentiation just fails. It just can't backpropagate through the code. And here's a nice example from the Quake 3 code from the 1990s, where we want to compute 1 over the square root of x, which is a very common operation in online games where you're trying to render graphics and you need to normalize vectors. So in other words, compute 1 over the square root of the length of a vector. And this is very efficient C code that was 4 times faster than using the standard library code at the time. But what it does is it uses a bit manipulation of the IEEE floating point representation of real numbers. And you can see that in lines 9 and 10 of this C function. So that's exploiting this, this representation, IEEE representation, and those particular steps in the code are non-differentiable. You can't differentiate through that. However, we know that the function 1 over the square root of x is differentiable, and in fact we can hand derive the gradient and write down that gradient. So this is an example where the mathematical function that we're computing is differentiable, but the code that we use to implement it in the forward pass is not differentiable, and so we can't use automatic differentiation. So we would, in this case, we would separate the forward and backward pass operations, and we could use the efficient code in the forward pass, and then we would just override automatic differentiation and write our own backward pass code to implement 1 over the derivative of 1 over the square root of x. So all of the nodes that I've been talking about so far in this computation graph, or these layers within a deep learning model, are what I'm going to call an imperative node. And this is borrowing from the naming in programming languages, where the input-output relationship is explicitly defined. So y is an explicit function of the input and parameters. But there's another type of node that we can think about, which we call a declarative node. And here the input-output relationship is specified as the solution to an optimization problem. So within the node itself, we're going to solve this optimization problem, and we're going to return the solution to the optimization problem as the output to the node. And the nice thing about imperative and declarative nodes is that they can coexist within the same computation graph or deep learning model. Now, here's a short example of, or a simple example of a deep learning declarative node. So let's say we wanted to perform global average pooling, where we're given as input a set of vectors and we want to compute their mean as the output. Well, we can define this using the imperative specification, where we just say y equals 1 over n times the sum of the input vectors. Or we can specify this using a declarative specification, where y is the argmin over all vectors u that minimize the sum of the squared deviation of u from each of the xi's. Okay, that's another way to specify the mean. Now, this doesn't look like we're making progress. The declarative specification looks more complicated than the imperative specification. But the nice thing about the declarative specification is that it can be very, very easily varied. So for example, we can make it more robust by replacing this L2 penalty with an arbitrary penalty function phi, and we now have a declarative specification for computing the robust mean of a set of vectors. And here phi can be a convex function, or it could be a robust function like Huber, or it could in fact be a non-convex function. And this is not easily done in the imperative specification. Okay, so just to sort of recap, a declarative node is a parametrized optimization problem where you can think of it as defining this sort of landscape over the input and output parameters, and then for each value of the input, we fix that input, and that defines an optimization problem which we're going to solve for the output. So for example, if we fix the input at this blue line, we get a particular objective that we minimize to get the output for that particular input. If we fix it at the red line, then we get another optimization problem, parameterized by x, and we minimize that optimization problem to get our output y for the node. And so the main question with these parameterized optimization problems is, how do we compute the derivative of the output y with respect to the input x? In other words, how do we differentiate through the argmin operator? So we saw already that if we have a closed form solution, such as we do for least squares, then we can compute the derivative of that closed form solution directly. Another solution is to automatically differentiate the forward pass code. So for example, if we had, say, a gradient descent procedure or something where each step in the forward pass is differentiable, then we can use automatic differentiation to just unroll the forward pass code and backpropagate through that optimization algorithm. The last approach is to use implicit differentiation on the optimality conditions, which I will now talk about. So let's have a look at an example of differentiating an unconstrained optimization problem. We're going to look at a parametrized optimization problem, which is a scalar problem. So f is from r by r to r, and we're going to assume that it's twice differentiable. And so y is going to be the minimum of this function f parametrized at fixed value x. Then for a non-zero Hessian d2f dy squared, we have that the derivative of y with respect to x is equal to minus the inverse of the Hessian times the mixed partial second derivatives of f with respect to x and y. Okay, the proof of this result is fairly straightforward. So we know that the derivative of an unconstrained minimization problem, the derivative of that objective vanishes at the solution. So the derivative of f with respect to y is equal to 0 at the solution. And now we can differentiate the left-hand side of that equation with respect to x. So the derivative with respect to x of the derivative of f with respect to y is going to be the quantity that I've shown there. It's the direct derivative plus the indirect derivative. And then if we differentiate the right-hand side, that's the derivative of 0 with respect to x, which is equal to 0. And equating these two and rearranging gives us the result that we're looking for. Now, if we have a constrained optimization problem, then things become a little bit more complicated. So here we're looking at the solution to an optimization problem where we're minimizing over a function f subject to equality constraints h of x comma u equals 0. And if we assume that the solution exists and that both the objective and equality constraint functions are twice differentiable in the neighborhood of the solution, and moreover that the rank of the derivative of the constraint functions is equal to q, so it's full rank, then we have this expression here for the derivative of y with respect to x. And the way we arrive at this expression is by differentiating the optimality conditions, which in this case is the fact that the Lagrangian function, the derivative of the Lagrangian function, vanishes at the solution. And details can be found in our paper on deep declarative networks. All right, so now I want to look at the optimal transport problem. So this is a very, very popular problem in computer vision and machine learning. It's optimal transport is used to measure the distance between probability distributions. It can also be used to find matches between two sets of items. So for example, if we have m items in one set and n items in another set, then we can define a cost matrix for matching the ith item in one set to the jth item in another set. And then the output of optimal transport is going to be this probability matrix, which tells us the probability of making matches, okay, based on the costs. It's often formulated as an entropic regularization problem, where we want to minimize the inner product between the cost matrix and this probability matrix, plus some regularization term, subject to row and column sum constraints on P, which make it a valid probability distribution. Okay, and so we can view this as optimizing this objective function subject to P being a doubly stochastic matrix or lie within the convex hull of permutation matrices. Now, it turns out that optimal transport, the solution to optimal transport takes a very particular form. So each of the entries in the P matrix, Pij, is going to equal alpha I times beta j times e to the minus gamma Mij. Okay, where gamma is the regularization strength and Mij is an entry in our cost matrix. And the values alpha I and beta j can be found very efficiently using the Sinkhorn algorithm. So we start by setting a matrix Kij equal to e to the minus gamma Mij, and randomly initialize alpha and beta to be n-dimensional positive vectors. And then we iterate until convergence, setting alpha and beta to be such that we normalize satisfy the row and column constraints. And if we keep iterating, we'll eventually arrive at we'll eventually converge and arrive at a solution where both the rows and the columns satisfy the constraints. And then our matrix P is just the diagonal of alpha times k times a diagonal matrix formed from beta. Okay, so each operation that we perform in the Sinkhorn algorithm is differentiable, and so we can use automatic differentiation to backpropagate through the Sinkhorn algorithm. Alternatively, we can use the implicit differentiation result that I showed previously. Here we're dealing with matrices, which are the optimization variables and data for our problem. And so we end up with tensors when we take derivatives of each of them with respect to each other. But we can just think of flattening out the quantities m and p into vectors, right? So we vectorize them, and then we just back to the standard linear algebra that we had before on these mn dimensional vectors. Now, I won't go through the derivative of the gradient. It's quite tedious, and you can find the results in our paper. But there is a very efficient way of computing these gradients, and I'm showing the final result here. And then some Python code. And again, if you go to my homepage or the Deep Declarative Networks website, you can find the full implementation of this code as well as the derivation for the gradients. We did experiments in profiling this code where we set up a small bi-level optimization problem where the upper level problem is to match an output probability matrix with some target matrix that we randomly generated. And the lower level problem is to solve a optimal transport problem. Okay, so the variables that we're optimizing this bi-level problem over are the cost matrix M. And so we're trying to find a cost matrix M that will give us a probability matrix that matches our target. So if we look at the running time over 1,000 iterations of this code, we can compare 3 different implementations of the backward pass. So the first implementation, which is shown by the blue dashed line, is automatically differentiating through the Sinkhorn algorithm. The second, which is the orange dot dashed line, is the implicit differentiation result, but where we compute full inverses over H. And then the green curve is implicit differentiation, where we make use of the structure of the problem to be able to implement efficient linear algebra ways of implementing the inverse of the Hessian matrix H. And so you can see here that if we use these linear algebra tricks, we can get much faster running time compared to automatic differentiation for different problem sizes. And we're showing here on the left the CPU, and on the right a GPU implementation where we're comparing running time to problem size, so lower is better. We also gain in terms of memory usage. So here we're showing the automatic differentiation approach in blue dashed compared to the implicit gradient solution in orange. On the left, we have a fixed size problem of 500 by 500, and we look at how the memory changes as a function of the number of iterations of the Sinkhorn algorithm. And you can see for automatic differentiation, because it needs to store intermediate results, the memory just keeps growing per iteration of Sinkhorn. Whereas for implicit differentiation, it stays constant. On the right-hand side, we're looking at how the memory grows as a function of problem size for a fixed number of Sinkhorn iterations. And again, for automatic differentiation, as the problem size grows, the amount of memory grows very quickly. Whereas for the implicit solution, the amount of memory only grows as large as it needs to store the matrices M and P. And it doesn't need any intermediate calculations. Okay, so in summary, optimization problems can be embedded inside deep learning models. We can backpropagate by either unrolling the optimization algorithm or using implicit differentiation of the optimality conditions. The former is easier to implement and it just requires automatic differentiation, but is very memory intensive and may not be possible if the forward pass algorithm uses non-differentiable steps. The latter requires a regular and strongly convex solution, so it needs for the inverse of H to exist. But it doesn't need to know how the problem was solved in the forward pass, and it doesn't need to store any intermediate forward pass calculations. It does, however, require careful implementation, because computing the inverse of H may be costly. This is a very active area of research in how we take differentiable optimization and embed them in deep learning models. So there are a number of questions that I've raised here that you can read about in our paper and on our website. And finally, I want to thank you for listening and give you this URL, deepdeclarativenetworks.com, which you can go to for more information on these topics and links to papers in this area.